After deriving the transport equation for liquid water and then for water vapor, now we want to derive the transport equation for air. However, for computational reasons, it works out better if we consider vapor plus air together as the gas phase and an equation for that phase instead of just air. Since in vapor plus air, air is still an independent quantity, the vapor plus air equation is still going to be an independent equation. Now, as before, we really need to stay mechanistic. So we want to talk about mechanisms for vapor plus air, total gas flow. And for total gas, we don't have molecular diffusion. Vapor diffuses in air, air diffuses in vapor. But when it's air plus vapor together, it's only flow. So we're only going to consider pressure-driven flow of the vapor plus air or the gas system. Recap that all different types of flux we had grouped into two parts or two types, diffusive and convective. So total flux in general would be given by diffusive plus convective fluxes added together. So in general, the mass flux equation we had derived to have the diffusive component and the convective component. Now here in the gas phase inside the porous media, so that's air plus vapor here, the gas phase is, we're considering it together, vapor plus air. So vapor can move in air, air can move in vapor, but the entire phase together can only flow. So it will only have the convective flux. So convective flux means it would be given by its velocity times the density of that gas phase. So that velocity is going to be given by Darcy's law. So this is now my mass flux of gas, and this part is the flux due to gas pressure. This other part is due to gravity, but gravity in case of gas flow we can most likely ignore it. So this is my velocity due to Darcy flow, that's this part here, multiplied by the gas density, that's this part here. So in other words, the mass flux for the total gas is just a convective flux velocity multiplied by, and so in other words, it's going to be this part, the Darcy velocity multiplied by the gas density. So like before, the mass flux of gas given by the gas density multiplied by the Darcy velocity is going to be substituted into the gas conservation equation. But before that, note that the gas density here is also related to the pressure. And so that is substituted into the gas conservation equation. So note the gas conservation equation is vapor plus air. That's why it also has a I dot, because that's the vapor generation. And so we're going to substitute for ngx from this equation. If I do that, then we get this one, del Cg del T plus del X of the substituted quantity. Okay. Now these details are presented elsewhere, but the concentration of gas can be related to the saturation of gas, Sg. And if I do that, then I get an equation for Sg. Now Sg, saturation of gas, in turn can be related to saturation of water. So finally, we have an equation that has saturation of water and the other quantity due to convection and evaporation. Note that before these transport equations for water, for example, we were solving for the saturation of water. So we already have an equation for saturation of water. So we're not solving this one for saturation of water. We are actually solving this equation for pressure. So this is actually the pressure equation. This equation gives us the pressure that is used to calculate velocities of the fluid phases in all the equations. So it's very important and it's very convenient to solve for the pressure. Finally, we write the equation in a general form, and again in this one, then the unknown that we're solving for is this velocity, which is written in terms of the pressure. So pressure is the unknown. This gives pressure. Back to our map that we are using to record these transport process phases and driving forces and so on. So in case of the vapor plus air system, it does not have diffusion, it only has flow. So it is under flow, and the driving force for the flow is gas pressure. It also has the evaporation term because it has vapor in it and vapor is generated. So then the gas equation, that's the vapor plus air, provides the pressure for the system. So this completes the transport equations, the mass transport equations, and they include the water, liquid water, and vapor, and this one vapor plus air. Liquid water solves for the saturation of liquid, the vapor equation solves for the saturation of vapor, and this last one, vapor plus air equation, solves for the pressure.